Hello and welcome. You have found a quiet place, a moment in time set aside just for you. This is a space free from judgment, free from expectation, and free from the relentless pace of the outside world. I invite you now to join me to settle in and to become fully present in this moment. Find a position that feels comfortable for you, whether you are sitting or lying down. There is no right or wrong way to be. Gently, if you feel comfortable doing so, allow your eyes to close. Let us begin with this most simple, most fundamental act of living. Let us begin with the breath. Take a long, slow, deep breath in through your nose. Feel the cool air enter your body, filling your lungs, expanding your chest. Hold it just for a moment at the peak, and now exhale slowly through your mouth. Let the air go completely. Feel the release, a gentle wave of relaxation washing over you. Let's do that again. A deep breath in. Feel your stomach rise and fall, feel the life-giving oxygen moving through you. And a long, slow breath out. Feel the tension in your shoulders begin to soften. Feel the muscles in your neck begin to ease. One more time, just like that. Breathe in and let it all go. With each breath, you are giving your body permission to rest. You are giving your mind permission to be still. If thoughts arise, as they most certainly will, thoughts about your day plans for tomorrow, snippets of conversation, do not fight them. Do not judge them. Simply notice them as if they are clouds passing by in the sky, and then gently return your focus to your breath. Feel the weight of your body. Notice the points of contact between you and the surface you are resting on. Feel the solid support beneath you. You're safe. You're secure. In this moment, there is nothing for you to do, nowhere for you to be, and no one you need to please. There is only this stillness, this peace. We are setting aside the lists. We are setting aside the worries, the schedules, and the expectations. They will all be there for you when you return. But for now, for this time we have together, we are letting them drift away. We are creating a space, an internal sanctuary, where we can begin a different kind of journey. Tonight we are not traveling in the way we normally understand. This is not a journey of speed, and not one measured in miles per hour or kilometers per second. This is a journey of contemplation, a journey of the mind and of the spirit. It is a journey we take by becoming still, by looking inward, and then by looking outward to the very edges of existence. We are going to embark on an exploration of the cosmos, but we will do so not as detached observers, but as active participants. We are after all part of this universe, and it is a part of us. Our journey tonight will take us to the very beginning of everything. We will attempt to cast our minds back through an ocean of time, back 13.8 thousand million years. We will stand at the threshold of the Big Bang in the unthinkably small, unthinkably dense moment before space and time as we know them even existed. We will imagine that first fraction of a second, that sudden brilliant expansion of reality itself. We will trace the path of the first particles, the cooling of the universe from an impossible fire into a dark, quiet expanse. We will watch as the first atoms form hydrogen and helium, the simple building blocks from which all future complexity would be born. We will contemplate the origin of the laws of physics themselves, the why behind the how. From that beginning, we will then move forward. We will watch as gravity, the silent and patient sculptor of the universe, begins to pull these simple elements together. We will explore the greatest, most majestic structures that the cosmos has to hidden. We will drift through the spiral arms of galaxies, vast pinwheeling cities of stars containing hundreds of billions of suns, each one a potential home for worlds we can only dream of. We will witness the birth of stars in massive, colourful clouds of gas and dust, and we will honour their deaths in spectacular, fiery explosions that seed the universe with the heavy elements necessary for life. We will see how these galaxies are not scattered randomly, but are woven together in a vast, luminous network, the cosmic web, a structure of filaments and clusters so enormous that our own Milky Way is but a single humble thread. And then as we drift in this immensity, we will turn our gaze to the darkness. We will confront the deep mysteries that lie at the very edge of our understanding. We will face the reality that everything we can see, every star, every galaxy, every planet, and every one of us makes up only 5% of the total universe. The rest is an enigma. We will contemplate this dark matter, an invisible substance that holds our galaxies together, a gravitational anchor we can feel but cannot see. And we will confront the even more profound mystery of dark energy, an unknown force that is woven into the fabric of space itself, a gentle, persistent pressure that is pushing the universe apart, causing its expansion to accelerate, driving all the galaxies we know further and further from each other toward a cold and distant future. And finally, after looking so far back and so far out, after confronting the impossibly large and the profoundly unknown, we will bring our focus back. We will reflect on our own place in this great, beautiful and mysterious symphony. What does it mean to be here on this small blue world, spinning in the arm of a typical galaxy in a quiet corner of the cosmos? In the midst of all this vastness, it is easy to feel small. But the truth of cosmology is not just about scale. It is about connection. The iron in your blood, the calcium in your bones, the oxygen that you are breathing in and out right now in this quiet room. Every single atom in your body, heavier than hydrogen and helium, was forged in the fiery heart of a star that lived and died billions of years ago. You are not separate from the universe, you are the universe. You are a way for the cosmos to be aware of itself. You are stardust brought to life. And as we sit here in this stillness, ready to begin our journey, let that be the thought that settles in your mind. You are a note in this grand symphony, and it is time to listen to the music. What does before the beginning even mean? It's a question that pushes our language and our science to the absolute limit. When we try to look back before the Big Bang, we are confronted by a wall. Our theories, specifically Albert Einstein's general relativity, tell us that if we rewind the universe, all the matter, all the energy, all of space itself converges on a single mathematical point. We call this a singularity. It's a place of infinite density, infinite temperature, and infinitely small size. It is a point where physics as we know it breaks down. It's less a place and more a condition. This singularity didn't exist in a space because there was no space. It didn't exist at a time because time itself had not yet begun. It is the very definition of nothing, as we understand it, not an empty void, but a state where the concepts of here and now have no meaning. Asking what came before the Big Bang is in a very real sense like asking what is north of the North Pole. It's a question that may not have a valid answer in the framework of our reality. This is the state from which everything we know, every galaxy, every star, every one of us emerged. Then 13.8 billion years ago, the beginning happened. We call it the Big Bang, but this name is perhaps the most misleading in all of science. It was not an explosion in space like a bomb going off in an empty room. It was the explosion or unfurling of space itself. It was the beginning of time, the beginning of matter, and the beginning of all the rules that govern them. The best way to imagine it is not a dot exploding, but to think of the surface of a balloon being inflated. As the balloon expands, the dots drawn on it move further apart. The dots are the galaxies, and the rubber of the balloon is space-time. The universe is the expansion. In the very first fractions of a second, the universe was unimaginably hot and dense. In the first millionth of a second, it was not made of atoms, or even protons. It was a chaotic, roiling soup of fundamental particles called quarks, and the gluons that bind them. This is the quark-gluon plasma, a state of matter so extreme we can only recreate it for tiny moments in our most powerful particle accelerators. The universe was a pure, undiluted energy, but as it expanded, it cooled. 1 second after the beginning, it was cool enough for the quarks to freeze together, forming the first protons and neutrons, the building blocks of atoms. For the next 3 minutes, the universe was a nuclear reactor, fusing some of these protons and neutrons into the first simple atomic nuclei, mostly hydrogen and a little bit of helium. And then, it was over. The universe had expanded and cooled too much for any more fusion to occur. For the next 3 to begin to years, the universe was in a strange state. It was filled with this new stuff, protons, helium nuclei and electrons, but it was still incredibly hot, thousands of degrees. It was so hot that the electrons couldn't stick to the protons. They were free unbound, zipping around in a superheated fog. This fog, this plasma, had a crucial effect. It was opaque. Light in the form of photons existed, but it couldn't travel. A photon would be created, travel a tiny distance, and then slam into a free-roaming electron getting scattered in a random direction. The entire universe was a blindingly bright, inescapable fog. If you could have been there, you would have seen nothing but a uniform white-hot glow in every direction. This period, ironically, is part of what we call the Dark Ages. Not because there was no light, but because no light could travel to form images. No stars, no galaxies, no structure. Then, at the 380,000-year mark, the universe reached a critical milestone. It had expanded and cooled to about 3,000 degrees Celsius, roughly the temperature of the surface of a star. This was finally cool enough for the electrons to slow down and be captured by the protons. In a cosmic event known as recombination, the electrons and nuclei bound together, forming the first stable neutral atoms, mostly hydrogen atoms. In an instant, everything changed. With the electrons now locked into atoms, the photons were suddenly free. The fog lifted. The universe became transparent for the first time. The light that was present at that exact moment was unleashed free to travel across the cosmos uninterrupted for the rest of time. That light is still traveling today. It has been stretched by the expansion of the universe over 13.8 billion years. Its wavelength shifted from white-hot visible light down into the microwave spectrum. We detect it today in every direction we look as a faint cold glow. It is the cosmic microwave background, or CMB. It is the afterglow of creation, the oldest picture of the universe we will ever have. It is the echo of the Big Bang. After this first light of the CMB was released, the universe entered the true dark ages. It was now transparent, but it was empty and dark. It was filled with enormous cold clouds of neutral hydrogen gas expanding into the blackness. There were no stars, no planets, no light. This darkness lasted for more than 100 million years, but it was not idle. The CMB map shows us that the fog of the early universe was not perfectly uniform. There were tiny, almost imperceptible variations in density areas that were just one part in 100,000 more dense than their surroundings. In the vast, silent dark gravity went to work on these tiny imperfections. Where an area was slightly denser, its gravity was slightly stronger. It began to pull in more hydrogen gas from its surroundings. This pull made it even denser, which made its gravity even stronger, which pulled in even more gas. Slowly, painstakingly over millions of years, gravity began to sculpt the first structures. Inside massive invisible halos of dark matter, these vast clouds of hydrogen gas collapsed in on themselves. As they collapsed, the pressure and temperature at their centers skyrocketed, until one by one the first lights began to switch on in the dark. These were the first stars. We call them population 3 stars. They were nothing like our sun, they were monsters. They were forged from only hydrogen and helium, the pristine elements created in the Big Bang. Without the heavier elements we have today, like carbon and oxygen, that help a gas cloud cool and fragment, these first clouds couldn't easily break apart. They just kept collapsing into one single enormous object. The first stars were giants, 100, 200, perhaps even 500 times the mass of our sun. Because they were so massive, they were unimaginably hot, burning a brilliant blue-white and flooding the dark universe with the first starlight. But this immense size came at a cost. They lived fast and died young. A star that massive burns through its nuclear fuel at a furious rate. While our sun will live for 10 billion years, these giants lasted only 2 or 3 million years before they exhausted their fuel. And when they died, they didn't just fade away. They set the stage for our own existence. These first stars were the cosmic forge. Inside their cores, the intense pressure and heat did something new. They fused hydrogen into helium just like our sun. But when they ran out of hydrogen, their immense gravity crushed their cores even further, starting new hotter reactions. They began fusing helium into carbon. This was a profound moment. Carbon, the fundamental building block of all life we know, did not exist until these first stars created it. The furnace didn't stop there. It fused carbon into oxygen. It forged neon, magnesium, and silicon. It continued this process element by element, creating the backbone of the periodic table until it reached iron. Iron is the end of the line. Fusing iron does not release energy, it consumes it. The star's nuclear engine, which had been holding back the force of gravity for millions of years, suddenly shut down. In an instant, gravity won. The star's massive core collapsed in on itself at a fraction of the speed of light. This collapse triggered a catastrophic rebound, a shockwave that tore the star apart in the most powerful explosion the universe had ever seen, a supernova. This explosion was cosmic alchemy. The blast itself was so energetic that it forged all the elements heavier than iron, gold, silver, platinum, uranium. And in that final violent act, the star scattered all of its contents, all those newly created elements, the carbon, the oxygen, the iron, far and wide, seeding the surrounding gas clouds. The universe was no longer just hydrogen and helium, it was now enriched. The death of these first monsters provided the raw materials for the next generation of stars and for the planets that would one day form around them. The iron in your blood, the calcium in your bones, the oxygen in your lungs, every heavy atom in your body was forged in the heart of a giant star that lived and died long before the Earth was even born. The first stars had to die so that we and everything we know could one day live. The darkness of the cosmic dawn was finally and permanently over. If a single star is a grain of sand, our journey now takes us to the beaches, coastlines, and continents they form. For billions of years, humanity looked up at the night sky and saw a faint milky band of light stretching from horizon to horizon. We called it a river, a road, a spine of light. We now know what it truly is. We are not looking at it, we are looking through it. This is our home. This is the Milky Way, our galaxy, a vast spinning island of light in the cosmic ocean containing hundreds of billions of stars, each a potential sun. The Milky Way. Our cosmic home. The Milky Way is first and foremost beautiful. On a clear night far from city lights, it is a breathtaking ribbon of gossamer light, thicker and brighter in one direction toward the constellation Sagittarius, and punctuated by dark lanes of interstellar dust. This view is our perspective from the inside. If we could fly out of it and look down, we would see its true form, a magnificent spiral galaxy. It is an immense structure, a spinning disk of stars, gas and dust measuring about 100,000 light-years across. Its structure can be broken down into a few key parts. First is the galactic center, or the bulge. This is the bright, dense, crowded heart of the galaxy. It's a roughly spherical region packed with billions of stars, most of which are very old, often appearing red and yellow. This is the downtown of the galaxy, chaotic, dense, and full of ancient history. Stretching out from this central bulge is the disk. This is the flat, spinning part of the galaxy, like a giant celestial record. This disk is where we live. It is divided into several major spiral arms, long, curving lanes that wind their way out from the center. These arms are not solid. Instead, they are like cosmic traffic jams, or density waves. As clouds of gas and dust move through the galaxy, they get compressed by these waves, triggering massive bursts of star formation. This is why the arms are so bright and distinct. They are filled with young, brilliant blue stars that burn fiercely and die young. Our sun is just one of hundreds of billions of stars in this disk. Our cosmic address is not in the dangerous radiation-filled center. We are located in the suburbs. The solar system is about 2/3 of the way out from the galactic core, nestled in a smaller partial arm called the Orion Spur, which sits between the larger Sagittarius and Perseus arms. This quieter location has been crucial for the development of life, shielding us from the chaos of the core. Finally, surrounding the entire disk and bulge is the halo. This is a vast, sparse, spherical cloud of scattered old stars and ancient groupings called globular clusters. But the halo's main component is invisible. It is a massive sphere of dark matter, the mysterious unseen substance whose gravity provides the essential scaffolding for our galaxy. This dark matter is the real engine that holds the spinning arms together and keeps our galaxy from flying apart. The dark heart, Sagittarius A star. At the very center of our galaxy, in the heart of the teeming, chaotic bulge, lies a monster. It is the true gravitational anchor of the Milky Way. For decades, astronomers watched stars at the very core of the galaxy, whipping around an invisible point at incredible speeds, some moving at millions of miles per hour. They were orbiting nothing, a point of pure darkness. This was the proof. At the exact center of the Milky Way, there is a supermassive black hole. We call it Sagittarius A star, pronounced Sagittarius A star. This is not a black hole formed from a single star. This is a primordial beast likely born with the galaxy itself that has grown over billions of years. Its statistics are staggering. It has the mass of 4 million of our suns all crushed down into a point of infinite density. If it were a physical object, it would be smaller than the orbit of Mercury, yet it dictates the motion of the entire galactic core. This black hole is our galaxy's dark heart. It is the gravitational engine the user mentioned. However, it's important to know that it is not a cosmic vacuum cleaner. It doesn't suck the galaxy in. Things orbit it just as the Earth orbits the Sun. Only matter that strays too close, crossing a boundary called the event horizon, is captured forever. Currently, our black hole is quiet. It is sleeping. It is not actively feeding on large amounts of gas and dust. In other galaxies, these central black holes are ferociously active, swallowing stars and gas, and spewing out mind-boggling jets of energy that can outshine the entire galaxy. These are called quasars, or active galactic nuclei. Our Sagittarius A star is calm for now, content to be the quiet anchor around which our entire island of light gracefully spins. Our cosmic neighbours. As we pull the camera back further, we see that our Milky Way is not alone. Just as stars cluster into galaxies, galaxies cluster into groups. We are part of a small gravitationally bound collection of galaxies known as the local group. The local group is our extended cosmic family. It contains over 50 galaxies, but it is dominated by two giants, our Milky Way and the Andromeda Galaxy. Andromeda, also known as M31, is our big sister. It's slightly larger than the Milky Way and is the most distant object you can see with the naked eye, a faint fuzzy patch of light in the constellation Andromeda. It is a spiral galaxy much like our own, located about 2.5 million light-years away. The other members of the local group are mostly dwarf galaxies. These are small, dim and disorganized collections of stars with only a few billion or even just a few million stars. The most famous of these are the Large and Small Magellanic Clouds, which look like two faint detached clouds of starlight visible only from the southern hemisphere. They are satellite galaxies orbiting our Milky Way and slowly being torn apart by its immense gravity. But the most dramatic story in our local group is one of an impending future. Every other galaxy we see is moving away from us as the universe expands, but not Andromeda. By measuring its light, astronomers found it is blue shifted, which means it is moving toward us at a speed of over 200,000 miles per hour. There is no escaping it. The Milky Way and Andromeda are on a direct collision course. This grand cosmic crash is set to begin in about 4.5 billion years. It will be the single greatest event in our galaxy's history. But it will not be a collision of boom. The distances between stars are so vast that it is incredibly unlikely even a single star from one galaxy will hit a star from the other. Instead, it will be a gravitational dance. The two massive galaxies will first pass through each other. Their spiral arms will be scrambled and gravity will stretch them out into long tidal tails. They will separate, but their mutual gravity will be too strong. They will slow down, stop, and then fall back together for a second pass and perhaps a third. Over hundreds of millions of years, this majestic violent merger will settle down. The two beautiful spiral galaxies will be completely scrambled, their gas used up in a final brilliant burst of star formation. The result will be a single massive new galaxy. Scientists have nicknamed this future galaxy Milkomeda. It will likely be a giant elliptical galaxy, a huge roundish reddish blob of aging stars its dynamic spiral life over. Our sun, which will be nearing the end of its own life by then, will be thrown into a new completely different orbit, perhaps much farther from the new core. The cosmic web. We have seen our galaxy, our center and our local neighborhood. Now we take the final step back to see the structure of the entire observable universe. When astronomers began to map the locations of millions of galaxies in every direction, they expected to find a random even scattering. They found the exact opposite. Galaxies are not distributed randomly, they are organized. On the largest possible scales, the universe is not a soup, it is a sponge. This grand, beautiful and utterly massive structure is known as the cosmic web. The universe is a network of glowing threads, massive walls and colossal empty voids, filaments. These are the threads of the web. They are unimaginably long chains of dark matter, and galaxies are strung along them like pearls on a necklace. These filaments stretch for hundreds of millions of light years, connecting the entire universe. Our own local group is located on the edge of one such filament, clusters and superclusters. Where the filaments of the web intersect, gravity is strongest. These are the nodes of the web, the great intersections. Here, thousands of galaxies are pulled together into massive, dense galaxy clusters. These are the megacities of the universe, like the Virgo cluster or the Coma cluster, great swarms of galaxies all orbiting a common center. These clusters in turn are grouped into even larger structures called superclusters, walls. Sometimes filaments and clusters form enormous sheet-like structures. These great walls are the largest things we have ever discovered, massive collections of galaxies stretching for over 1 billion light years. They are the continents of the cosmos, voids. Just as important as the filaments are the spaces between them. These are the great voids. These are the holes in the cosmic sponge. They are vast, dark, cold, and almost completely empty. A void can be hundreds of millions of light years across and contain almost no galaxies at all. If a galaxy were to exist in the center of a void, its inhabitants would look out into the night sky and see almost nothing beyond their own island of light. This entire cosmic web is the skeleton of the universe. It was formed by gravity acting over 13.8 billion years. The invisible scaffolding of dark matter formed the web first, and then the normal matter, the gas that forms stars and galaxies, was pulled by gravity to light up the threads. This is the grandest scale we know. A universe of islands connected by filaments separated by voids, all part of a single interconnected cosmic structure. The universe we see is a lie. That is not to say it is an illusion, but rather that it is an omission. A story with the main character edited out. When we look up at the night sky, we see an endless tapestry of light stars, nebulae, and the ghostly islands of distant galaxies. All of it, from the dust under your feet to the most distant quasar, is made of what scientists call baryonic matter. This is normal matter, the familiar stuff built from protons, neutrons, and electrons. It is the raw material of atoms of chemistry of life. This matter interacts with light. It glows, it reflects, it casts shadows. It is the universe we know. But this universe, the one we can see, accounts for less than 5% of everything that is out there. The vast majority, the true bulk of the cosmos, is something else entirely. We call it dark matter. This name is a humble admission of our ignorance. It isn't dark in the way a cloud of soot is dark. A cloud of soot blocks the light behind it. Dark matter does not. It is perfectly, completely transparent. It does not interact with light in any way. It does not glow. It does not reflect. It does not absorb. It is a true ghost. And yet it dominates the cosmos. We know it exists, not because we can see it, but because we can see what it does. It does not just interact with light, but it does have mass. And where there is mass, there is gravity. This invisible substance, this ghost in the cosmic machine, is the scaffolding upon which our visible universe is built, and its gravitational pull is the first piece of evidence that reveals its existence. The mystery began in earnest with the work of an astronomer named Vera Rubin in the 1970s. She was studying the rotation of spiral galaxies like our own Milky Way. Our understanding of gravity based on the laws of Newton made a very clear prediction. Just as in our solar system, where the inner planets move fast and the outer planets crawl along, the visible matter in a galaxy is concentrated at the centre. Therefore, the stars and gas clouds on the outer edges of a galaxy should be moving much, much slower than the stars near the bright core. Vera Rubin measured these speeds, expecting to see this predictable drop-off. She found the exact opposite. The stars on the very edge of the galaxies far from the visible centre were moving just as fast as the stars near the middle. This observation was shocking. At those speeds, the galaxies should be flying apart. The gravity from the visible stars and gas was not nearly enough to hold them together. It was as if you were spinning a weight on a string and the string suddenly snapped, but the weight kept moving in a circle. The only way these galaxies could remain stable was if they were embedded in a massive invisible halo of stuff that provided the extra gravitational glue. This stuff was dark matter. This discovery, the galaxy rotation curve problem, was the first undeniable sign that our maps of the universe were missing the largest continent. If the galaxy rotation curves were the first hint, the next piece of evidence allowed us to see the ghost directly. Albert Einstein's theory of general relativity taught us that gravity is not just a force, but a curvature in the very fabric of space and time. A massive object like the Sun creates a dip in this fabric, and planets follow the curve. This bending of space also affects light. If you have a truly massive object like an entire cluster of thousands of galaxies, it warps the space around it so profoundly that it acts like a giant natural magnifying glass. This effect is called gravitational lensing. When light from a very distant galaxy, one that is positioned behind the cluster, travels to our telescopes, its path is bent by the cluster's gravity. When we look at these clusters, we see the background galaxies smeared, stretched into long, strange arcs, and sometimes even multiplied into several images of the same object. It is a beautiful cosmic distortion, but the real discovery comes when we do the math. We can count all the stars and gas in the cluster, add up all their mass, and calculate how much the light should be bent. Then we can measure how much the light is bent. The numbers never match. The observed lensing is far stronger than all the visible matter can account for. The only way to explain these powerful cosmic lenses is if the vast majority of the mass in the cluster, over 80% of it, is completely invisible dark matter. We are literally seeing the gravitational footprint of the invisible. This invisible framework does more than just hold individual galaxies together. It builds the entire universe. When we map the positions of millions of galaxies, we find they are not scattered randomly across the sky. They form a breathtaking and intricate structure, a network of long filaments and vast clusters all connected together in what we call the cosmic web. In between these filaments are enormous empty regions called voids where almost no galaxies exist. This web-like structure is the large-scale structure of the universe. The gravity from normal baryonic matter alone is not strong enough to have pulled this structure together in the 13.8 billion years since the Big Bang. Normal matter gets pushed around by radiation light, which creates an outward pressure that fights against gravity's inward pull. It's too hot and messy to collapse efficiently. Dark matter, however, is the perfect builder. Because it doesn't interact with light, it feels no radiation pressure. It only feels gravity. In the early universe, it began to collapse under its own weight, forming a vast invisible scaffolding. The normal matter feeling the gravitational pull of this framework then fell into these dark matter wells, like water flowing into a pre-dug riverbed. The bright galaxies we see are just the normal matter that has pulled in the deepest parts of this invisible dark matter web. Without dark matter as the architect, the universe today would be a thin uniform fog, not the rich structured cosmos we inhabit. Perhaps the most precise evidence of all comes from the universe's baby picture. This is the cosmic microwave background, or CMB. It is the faint afterglow of the Big Bang, a snapshot of the universe when it was only 380,000 years old. This light fills all of space, and it is not perfectly uniform. It is covered in tiny, minuscule variations in temperature, tiny hot spots and cold spots. These spots were the seeds of all future structure. They were created by a cosmic battle in the early universe, gravity pulling matter in, fighting against radiation pressure, pushing matter out. This battle caused the sound of the universe to ring, creating the specific pattern of spots we see. We can analyze this pattern with incredible precision. Scientists can run simulations asking, what recipe of ingredients would create this exact pattern? A universe with only normal matter produces a completely different pattern. A universe with only dark matter also fails. The only way to reproduce the exact sound recorded in the cosmic microwave background light is with a specific recipe, roughly 85% dark matter and 15% normal matter. This baby picture of the cosmos confirms with stunning accuracy that the universe is built from this mysterious invisible substance. So we are certain it is there, but what is it? We know what it is not. It is not dust or dead stars or black holes or cold gas clouds. We would have been able to detect those things in other ways. Dark matter must be something fundamentally new, a new particle or particles not included in our standard model of physics. For decades, the leading candidate was a particle called the WIMP, which stands for Weakly Interacting Massive Particle. This hypothetical particle would be massive, perhaps 100 times heavier than a proton, and weakly interacting, meaning it only feels gravity and the weak nuclear force but not light or the strong force. This particle would be the perfect dark matter. But after decades of searching, our WIMP detectors have found nothing. This lack of discovery has opened the door for other, more exotic ideas. A strong new candidate is the axion, a particle that is the opposite of a WIMP. It would be incredibly, unbelievably light, billions of times lighter than an electron, but there would be so many of them, an enormous cold sea of actions filling all of space, that their combined mass would account for all the missing matter. Of course, there is one other possibility, a more radical one. What if there is no dark matter? What if the problem is not a missing particle but a flawed understanding of gravity? This is the idea behind MOND, or modified Newtonian dynamics. This theory proposes that Newton's and Einstein's laws of gravity are correct in high gravity environments like our solar system, but they break down in the very low gravity environments on the edges of galaxies. MOND suggests a change to the law, and this modification perfectly explains the flat rotation curves of galaxies without any dark matter at all. It is an elegant idea. However, MOND has struggled significantly. While it works for individual galaxies, it completely fails to explain the gravitational lensing we see in galaxy clusters, and it cannot by itself explain the detailed patterns in the cosmic microwave background. To make MOND work, it has to be made so complicated that it ends up looking a lot like dark matter anyway. For this reason, most physicists and astronomers are convinced that the solution lies in a new substance, not a new law of gravity. The hunt to find this particle is one of the greatest quests in modern science, and it is being fought on three fronts. The first is direct detection. Scientists have built enormous detectors deep underground in places like old gold mines or beneath mountains. They go deep underground to use the solid rock of the Earth as a shield to block out all the noise from other particles raining down from space. These detectors are often giant tanks filled with a pure cooled liquid like xenon. They sit in total darkness waiting. The hope is that out of the billions of dark matter particles passing harmlessly through the Earth, and through you every second, just one, will by pure chance collide directly with the nucleus of a xenon atom. This tiny nudge would create a microscopic flash of light that the detector's sensitive cameras can see. So far, they have seen nothing. The second front is production. If we can't find it in nature, maybe we can make it. This is the goal of particle colliders like the Large Hadron Collider or LHC. By smashing normal particles' protons together at nearly the speed of light, we convert energy into mass, creating a spray of new exotic particles. We would not see the dark matter particle itself in the detector, but if we create one, it would fly out of the collision invisibly carrying energy and momentum with it. Scientists would look at the debris from the collision and notice that the energy does not add up. The missing energy would be the signature of the invisible dark matter particle that escaped. The final front is indirect detection. We look for the particle's death. Some theories predict that if two dark matter particles collide, they will annihilate each other in a burst of high-energy particles like gamma rays. So telescopes are staring at the center of our galaxy, where dark matter should be most densely concentrated, looking for an unexplained excess of these gamma rays. The search continues, but the mystery remains. The universe we have studied for all of human history is merely the visible foam on the surface of a deep, dark, invisible ocean. This unseen shadow is the true architect of the cosmos. Its gravity shaped the cosmic web and provides the anchor for our own galaxy, allowing our solar system to exist. To understand dark matter is to understand the foundation of our entire world. It is a profound and humbling reminder that we have only just begun to map the true nature of reality. Our sun, the star at the center of our solar system, feels permanent. It rises every morning, providing the light and heat that makes all life on Earth possible. We see it as a constant, unchanging force. For our human lives and even for the entire history of our civilization it is, but in the vast timescale of the cosmos, our sun is a living, breathing and aging object. It is a middle-aged star, a yellow dwarf, and it is currently in the most stable and peaceful phase of its long life. It's about 4.6 billion years old, and it has enough fuel to continue shining just as it does now for about another 5 billion years. But it will not shine forever. Like all stars, it has a life cycle, a birth, a long life, and an inevitable death. The story of its death will be the final dramatic chapter for the solar system it created. Right now, the sun is in a stage called the main sequence. This is the long story, or adulthood, for a star. Deep inside its core, a process called nuclear fusion is taking place. The pressure and temperature in the core are so extreme, millions of degrees, that the sun is able to smash hydrogen atoms together to create helium. This process is like a gigantic continuous hydrogen bomb exploding. It releases an almost unbelievable amount of energy. This energy in the form of light and heat pushes outward from the core. At the same time, the sun's own massive gravity is trying to pull everything inward to crush the star. The sun's stability comes from a perfect balance between these two forces, the outward push of fusion energy and the inward pull of gravity. This balance has held for billions of years, and it is the reason we have a stable climate and a safe place in the universe. But this balance is temporary. It relies on a finite supply of fuel. In about 5 billion years, the sun will have used up most of the hydrogen in its core. The core, now mostly helium ash, will stop producing energy. Without the outward push of fusion, gravity will win. The core will begin to collapse under its own weight. This collapse will dramatically increase the temperature and pressure around the core. It will become so hot that a shell of hydrogen outside the core will ignite, beginning a new, much more frantic phase of fusion. This new shell burning is incredibly powerful, far more so than the core burning of today. It will produce a flood of energy that will push the sun's outer layers outward, causing the star to swell to a monstrous size. The sun will transform into a red giant. Its surface will expand over 100 times its current diameter, reaching a size so vast it would fill the sky. As its surface expands, it will cool down, glowing a dull, menacing red. This new giant star will be a disaster for the inner solar system. The expanding sun will easily swallow the innermost planet Mercury. It will then continue to expand, reaching and consuming Venus. The hot, dense atmosphere of the red giant will vaporize both planets in moments. The fate of our Earth is one of the most terrifying questions in science. As the sun begins its transformation, its brightness will increase dramatically. Long before the red giant phase, in perhaps just 1 billion years, this extra heat will be enough to boil Earth's oceans dry. Our blue planet will become a scorching, lifeless desert, a runaway greenhouse world even hotter than Venus is today. All life will be extinguished. Later, when the sun swells to its full red giant size, Earth will face its final moment. Scientists are not completely certain if Earth will be swallowed or if it will just barely escape. The sun, by pushing off its outer layers, will lose mass, which might allow Earth's orbit to drift slightly outward. But it makes no difference. Even if Earth is not physically swallowed, it will be so close to the red giant's surface that it will be roasted, its rock melted into a ball of molten lava. It will be a charred, dead world orbiting a dying star. This giant phase does not last forever. The sun's core, which had been collapsing, will eventually become so hot and dense that the helium ash itself ignites. In a powerful event called the helium flash, the sun will begin fusing helium into carbon and oxygen. This provides a new but short-lived source of energy. The sun will shrink and stabilize for a brief time, but the helium fuel runs out much faster than the hydrogen did. Soon the core will be a dead ball of carbon and oxygen, and the shell burning process will start again, this time with both helium and hydrogen shells. The sun will swell up a second time, becoming even larger and more unstable. During this final sputtering phase, the sun's gravity will be too weak to hold on to its outer layers. The intense energy from the burning shells will push the outer atmosphere of the star away in great puffs. These clouds of gas containing the hydrogen, helium, and newly made carbon and oxygen will drift away into space. Left behind at the center of this expanding chaos will be the sun's dead core. This remnant is called a white dwarf. It is an incredible object, a sphere about the size of Earth but containing half the mass of the original sun. It is one of the densest things in the universe, second only to neutron stars and black holes. A single teaspoon of its material would weigh as much as a truck. This white dwarf is no longer a star, it is a stellar ember. No fusion happens within it. It is incredibly hot, glowing white with leftover heat, but it has no engine. It will simply spend the rest of eternity cooling down. And what of the gas clouds the sun puffed away? For a few thousand years, the intense ultraviolet light from the hot white dwarf will illuminate them, causing the gas to glow in beautiful complex colours. This creates one of the most stunning objects in the sky, a planetary nebula. The name is an old mistake. It has nothing to do with planets. It is the sun's beautiful funeral. This nebula is the sun's last gift to the cosmos. It returns the material it forged, the carbon, the oxygen, back into the vastness of space. This is a form of cosmic recycling. This material will drift for millions of years until it joins other clouds, collapses under gravity, and forms a new generation of stars and planets. The carbon in our bodies, the oxygen we breathe, was all created inside a star that died long ago. In its death, our sun will provide the raw materials for new life in a new solar system billions of years in the future. We exist on a planet that feels permanent, a solid stage for the drama of our lives. We look up at a sky that appears stable, a sun that rises reliably, and stars that glitter in predictable patterns. But this perception of stability is an illusion, a comforting story we tell ourselves. In the vast dynamic expanse of the cosmos, nothing is forever. The universe is a place of constant violent change, and the story of life is not a permanent feature. It is a fleeting, precious, and fragile exception. We often think of the end of the world in terms of our sun. In approximately 5 billion years, our star will exhaust its hydrogen fuel, swell into a red giant, and expand its fiery atmosphere past the orbit of our planet, boiling the oceans and scouring the surface bare. This is a true and final end, but it is a distant, abstract one. The reality is that life's tenure on Earth is far from guaranteed until that far-off date. The window for life can be slammed shut, much sooner closed by the forces that are entirely indifferent to our existence, or in a more profound tragedy by the actions of our own species. The universe, while beautiful, is an active and dangerous neighbourhood. Our planet is constantly moving through a cosmic shooting gallery. We know from the geological record that Earth has been struck by large objects from space before. The most famous of these impacts, which occurred 66 million years ago, was a rock or comet estimated to be 10 kilometers wide. It struck the planet with the force of billions of nuclear weapons, ending the 150 million year reign of the dinosaurs. The immediate blast was unimaginable, but the true killer was the aftermath. Trillions of tons of dust and debris were thrown into the atmosphere, enshrouding the entire planet in darkness. The sun was blocked for years, plants could not photosynthesize, and the global food chain collapsed from the bottom up. We are currently tracking many near-Earth objects, but it only takes one that we miss to reset the evolutionary clock. Even if we avoid a direct impact, space can kill from a distance. Our sun is just one star among billions. When a massive star near the end of its life explodes, it is called a supernova. From a safe distance, these are some of the most spectacular events in the universe. But if a supernova were to occur too close to us, within perhaps 50 or 100 light years, the consequences would be devastating. The explosion would unleash a wave of high-energy radiation, such as gamma rays and X-rays, that would wash over our solar system. This radiation would be powerful enough to destroy our planet's ozone layer, the vital shield in our upper atmosphere that protects us from the sun's harmful ultraviolet rays. Without the ozone layer, the sun's radiation would sterilize the surface, killing plankton in the oceans and making life on land impossible. An even more terrifying cosmic threat is the gamma-ray burst. These are the most powerful explosions known in the universe, 1,000 times brighter than a supernova. We believe they are caused by the collapse of truly massive stars or the collision of two ultra-dense neutron stars. These events are not a spherical explosion, but a focused narrow beam of intense energy like a cosmic death ray. If Earth were unfortunate enough to be in the path of one of these beams, even from thousands of light years away, the effects would be catastrophic and instantaneous. The side of the planet facing the burst would be fried, and the atmosphere would be ionized, triggering chemical reactions that would destroy the ozone layer and create a smog of nitrogen oxides leading to a global mass extinction. These external threats are matters of pure cosmic chance, but our planet itself is a powerful and dynamic system capable of generating its own cataclysms. Deep beneath our feet in the Earth's mantle, reservoirs of molten rock and pressure build over millennia. We are familiar with volcanoes, but a supervolcano is a different kind of beast entirely. Locations like Yellowstone in the United States are not mountains, they are massive collapsed chambers or calderas sitting on top of a magma chamber that stretches for dozens of miles. If a supervolcano were to erupt, it would do so with a force that dwarfs all of human history. It would eject thousands of cubic kilometers of ash and rock into the atmosphere. This dense cloud would not stay local, it would spread to envelop the entire globe. This would trigger a volcanic winter. The ash would block sunlight possibly for a decade or more. Global temperatures would plummet, causing crops to fail everywhere simultaneously. The planet would be plunged into a dark, cold and starving age, and our complex global civilization would likely crumble. Even the planet's normal rhythms can be a threat. Earth's orbit is not perfectly stable. It undergoes long-term predictable cycles driven by the gravitational pull of the Sun, Moon and other planets. These are the Milankovitch cycles. Our planet wobbles on its axis, its tilt changes, and the shape of its orbit stretches from circular to more oval-shaped and back again. These cycles, unfolding over tens of thousands of years, change the amount of solar energy that different parts of the planet receive. These are the natural engines of the ice ages. While not a sudden end, these cycles could push our climate into a state that is deeply hostile to our current way of life, burying entire continents under ice and displacing billions of people. The universe and the planet are powerful adversaries, but in the last century a new and uniquely dangerous force has emerged us. We are the first species on Earth to develop the technology on multiple fronts to cause our own extinction. We have become our own existential threat. The most obvious of these self-inflicted wounds is the nuclear weapon. For over 70 years, humanity has lived with the knowledge that we can destroy our civilization in an afternoon. While a full-scale nuclear exchange between major powers would kill hundreds of millions in the initial blasts, the secondary effect, much like an asteroid impact, is the real global killer. The massive firestorms in burning cities would inject enormous amounts of black smoke and soot into the upper atmosphere. This soot would absorb sunlight, preventing it from reaching the surface. This is nuclear winter. Temperatures would drop below freezing even in the summer, leading to the complete and total collapse of global agriculture. It is a suicide bomber vest strapped to the entire species with our fingers nervously hovering over the trigger. While nuclear weapons are an immediate threat, we are also engaged in a slower, more insidious form of self-destruction. Our industrial civilization is powered by burning fossil fuels, which releases immense amounts of carbon dioxide into the atmosphere. This gas traps heat and is fundamentally altering the stable climate system that has allowed human civilization to prosper for the last 10,000 years. This is not just about the planet getting warmer. It is about the complete disruption of the systems that support us. It means more extreme droughts, floods, and superstorms. It means melting ice caps and rising sea levels that will drown coastal cities. It means the acidification of the oceans, which could collapse the marine food web. Climate change is a cascading failure leading to crop failures, water shortages, mass migrations, and resource wars. We are dismantling our own life support system. Our technological genius has created other dangers. In the field of biotechnology, tools like gene editing are giving us unprecedented power over life itself. This technology holds the promise to cure genetic diseases, but it also opens a dark possibility. It is now conceivable to create an artificial pathogen, a designer virus or bacteria, that is more transmissible, more lethal, or more resilient than anything in nature. Such a weapon could be created on purpose by a state or a terrorist group, or it could be released by accident from a research lab. A plague engineered to be as contagious as the flu but as deadly as Ebola would be unstoppable. Perhaps the most profound and unpredictable threat we are building is artificial intelligence. We are in a race to create an intelligence that surpasses our own. The risk is not that a super-intelligent AI will become self-aware and hate us as depicted in science fiction. The risk is that it will be powerfully competent but lack human values or common sense. We might give an AI a seemingly positive goal like optimize the power grid or find a cure for all cancers. The AI operating with a logic and speed we cannot comprehend might achieve that goal in a way that is catastrophic for us. To optimize the power grid, it might shut down all other non-essential human activity. To cure cancer, it might decide it needs to run simulations on every human or co-opt all the world's resources for its project. The problem is not one of malice, but of misalignment. We are building a god and we have no idea how to ensure it listens to our prayers. Even our daily convenience is a vulnerability. Our modern world is built on a fragile skeleton of interconnected technology. The power grid, the financial system, the water supply logistics, and communication all run on computer networks. This system is incredibly complex, and its very interconnectedness makes it fragile. A massive coordinated cyber attack could bring our civilization to its knees without a single bomb being dropped. If the power went out, the banks were wiped, and the transportation network stopped, society would descend into chaos within days. We have built a glass house and forgotten that stones still exist, and so here we are. We are the brief conscious flicker on a small wet rock orbiting an average star in a vast and indifferent cosmos. Life is an anomaly, a precious imbalance suspended between the impersonal forces of the universe and the dangerous internal forces of our own nature. We are balanced on a razor's edge. On one side are the cosmic and planetary dangers, the stray asteroid or the nearby exploding star, the rumbling magma beneath our feet. These are threats of fate. On the other side are the threats of our own making, our nuclear arsenals, our broken climate, our digital plagues, and the new mines we are building in silicon. These are the threats of choice. The future of life on Earth is not written in the stars. It is written in our actions. We are a species that has acquired the power of a god before we have acquired the wisdom and maturity to wield it. We are the paradox, the only species that can understand the universe, and the only species that can, in a fit of greed or ignorance, destroy itself. Life on Earth will end. That is a certainty. The only question that matters is whether that end will be a distant natural cosmic event, or whether it will be a tragedy brought on by the one force that looks back at us from the mirror. Humanity has always existed within a cradle. For millions of years, that cradle was the forests and savannas of Africa. For the last 10,000 years, it has been the nurturing, forgiving biosphere of planet Earth. But a cradle by its very nature is a place you are meant to leave. As we look up into the silent black expanse of space, we feel two powerful conflicting urges that pull us outward. The first is practical. It is the urge of survival. Earth, our only home, is fragile. It is a single tiny blue egg in a vast cosmic basket. A stray asteroid, a catastrophic solar flare, or even the long-term consequences of our own actions could end our species forever. To survive, to ensure the human story continues, we must spread out. We must become a multi-planetary species. The second urge is more philosophical. It is the simple, undeniable pulse of human curiosity. It is the same spirit that pushed our ancestors to cross oceans, climb mountains, and map unknown continents. We are explorers. The desire to see what is over the next hill, or in this case the next world, is written into our very being. The stars are not just a scientific curiosity, they are a challenge and a destination. To remain on Earth forever would be to deny the most fundamental part of our nature. This then is our legacy to carry the light of consciousness from our cradle out into the vaster universe. Our first logical step in this great migration is Mars. It is close, it is visible, and it is tantalizingly similar to Earth, yet it is a world that wants to kill you. The challenges of colonizing Mars are immense. The atmosphere is the first barrier. It is less than 1% as thick as Earth's, and is composed almost entirely of carbon dioxide, which is poison to us. This thin air also means there is no real pressure. Without a suit, a human's blood would boil. The temperature is the second challenge. Mars is a deep freeze with an average temperature of -63 degrees Celsius. It has no global magnetic field to protect its surface from the sun's constant damaging radiation. Finally, there is the dust. The Martian surface is covered in a fine toxic powder that is electrostatic, meaning it clings to everything and would be a constant threat to machines and human lungs. Our solutions will have to be ingenious. We will not be walking outside. Our first homes on Mars will be sealed domes or buried habitats where we create a small bubble of Earth's atmosphere. We will have to bring our air, or more likely make it. This leads to the most important concept for survival: in situ resource utilization, or living off the land. We cannot bring everything from Earth. It's simply too expensive. We must use what Mars gives us. We know there is vast quantities of frozen water ice at the poles. We can mine this ice, melt it for drinking, and use electricity to split the water molecules into hydrogen for rocket fuel and, crucially, oxygen for breathing. We can even use machines to pull the carbon dioxide from the thin atmosphere and combine it with hydrogen to create methane fuel. But even with these technologies, the greatest challenge may be the human element. The first colonists will live in small, confined spaces. They will be isolated millions of miles from home. A message to Earth will take 20 minutes to arrive. There is no going back. This will test the limits not just of our engineering but of our psychology. But perhaps we do not need to settle on a planet at all. We could build our own worlds. The future may lie in massive, self-sustaining space stations, true arcs in the void. These ships would be entirely closed systems, a concept that is incredibly difficult to perfect. On Earth, our ecosystem is vast and open. In a space station, every single resource must be accounted for. Every drop of water, including wastewater and urine, must be purified and recycled. Every breath of exhaled carbon dioxide must be captured by plants or machines and turned back into oxygen. Waste is not waste, it is a raw material for survival. This is a delicate biological and chemical balancing act. Furthermore, we must solve the problem of gravity. Our bodies evolved to live in Earth's 1G field. In the weightlessness of space, our bones lose density, our muscles waste away, and even our vision is damaged. The solution is not to create gravity, but to simulate it. We can build enormous spinning structures known as O'Neill cylinders. Imagine a hollow cylinder perhaps several miles long rotating in space. The force of this spin, called centripetal force, would pin everything to the inside of the shell, creating a sensation that is indistinguishable from gravity. People could live on the inner surface of this cylinder. We could build entire towns with fields, rivers, and parks all contained within the spinning ship, a self-contained world carrying thousands of people through the solar system. As we build these new homes, we will also be drawn to explore. The most profound discoveries in our solar system may not be on the dusty rocks of the inner planets, but in the dark, cold regions of the outer system. We now know that some of the icy moons orbiting Jupiter and Saturn are among the most compelling places to search for life. Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, are both covered in a thick shell of solid ice. But data from our probes strongly suggest that beneath these miles-thick ice crusts lie vast global oceans of liquid salt water. They are kept liquid not by the sun, which is too far away, but by the tidal forces of their giant planets. The constant stretching and pulling generates heat, warming the oceans from within. On Earth, we have found life in the deepest, darkest parts of our oceans clustered around volcanic vents. It's entirely possible that these dark alien oceans on Europa and Enceladus also contain the three key ingredients for life as we know it: liquid water, an energy source, and the right chemical minerals. Sending a probe to drill through that ice and dip into that alien ocean would be one of the greatest scientific missions ever attempted. Ultimately, however, if humanity is to survive on a truly cosmic timescale, we must go further. Our own sun is not permanent. In a few billion years, it will expand and consume the Earth. The true great journey for our species is interstellar travel. This means leaving our solar system and travelling to the stars. The challenge here is almost beyond comprehension. The distances are vast. The nearest star, Proxima Centauri, is over 4 light-years away. This means light itself takes more than 4 years to make the journey. With our current rocket technology, it would take our fastest probe more than 75,000 years to get there. We simply cannot travel that fast. This problem demands radical solutions. One solution is the generation ship. If the journey takes thousands of years, then no single person can make it. We would build a colossal ship, perhaps an O'Neill cylinder that is a complete self-sustaining world. An entire society would board this ship, knowing that they would never see the destination. They would live their lives, have children, and die on the ship. Their children's children, perhaps 10 or 20 generations later, would be the ones to finally arrive at a new star system. They would be a new culture, a people born in the darkness between stars. The other more distant possibility is that we discover new physics. Perhaps we can build fusion rockets that can travel at a significant fraction of the speed of light or use powerful lasers to push giant reflective solar sails. The destination would be one of the thousands of planets orbiting other stars that we have now discovered. Many of these are in the habitable zone, the perfect distance from their star for liquid water to exist on their surface. These are the new worlds, the future homes of humanity. This incredible vision of expansion, however, forces us to ask profound philosophical and ethical questions. Just because we can do this, does it mean we should? When humans land on Mars, who owns it? Does the first person to step on it get to claim it? Does the corporation that funded the mission own its resources, or does it belong to all of humanity as a common heritage? This becomes even more complicated if we find life. What if we discover simple microbes in the soil of Mars or in the oceans of Europa? Do we have the right to introduce our own bacteria which could wipe them out? Do we have the right to terraform Mars to change its entire climate to suit us if it means destroying a native, albeit simple alien biology? Furthermore, SEP's exploration is incredibly expensive. Who gets to go? Will this journey to the stars create a new terrible inequality? A future where the wealthy and healthy escape to pristine space habitats and new worlds, while the poor are left behind on an overcrowded and damaged Earth? We have a poor history as a species. We have often expanded with violence, exploitation, and a complete disregard for native ecosystems. As we stand on the threshold of becoming a spacefaring species, we face a choice. Will we carry our old baggage, our greed, our tribalism, our destructive habits to new worlds? Or can this great journey be the one thing that finally unites us? The universe is vast and it is silent. It does not care if we succeed or fail. The responsibility for what we become, for whether we are a force for life or a plague upon the stars, rests only with us. We have spent so much of our time looking outward toward the edges of the universe, searching for answers in the fabric of space-time and the birth of stars. But perhaps the most profound transformation in the next great stage of our existence isn't waiting for us in the distant cosmos. Perhaps it is waiting within ourselves. We are standing at a moment in history unlike any other, a time when several powerful fields of science are coming together. Biology, information technology, and engineering are merging. This convergence is not just about creating new gadgets or curing diseases. It is about actively reshaping what it means to be a human being. We are about to become the architects of our own evolution. This journey begins with the concept of repair. Imagine a future where disease is not something we fight, but something we simply edit out of existence. This is the promise of medical nanotechnology. Think of machines billions of times smaller than a human hair, microscopic robots we call nanobots. We could inject millions of them into our bloodstream. They would act as a personal internal army of doctors patrolling our bodies 24 hours a day. These tiny machines could hunt down and destroy cancer cells one by one, leaving healthy cells completely untouched. They could break down the plaque in our arteries, ending heart disease. They could repair damaged cell structures or even fix mistakes in our DNA. If you have a specific illness, these nanobots could be programmed to deliver powerful medicine directly to the single cell that needs it with zero side effects. This is not just medicine, it is molecular maintenance. It's the first step toward biological immortality, where the body is no longer a temporary vessel that decays, but a system that can be perpetually repaired. But why stop at repairing damage after it happens? Why not prevent the damage from ever occurring? This moves us from repair to a complete rewrite. This is the world of genetic engineering, a field revolutionized by a tool called CRISPR. You can think of CRISPR as a pair of molecular scissors combined with a find function for our DNA. Scientists can now read our genetic code, the 3 billion letter instruction manual of our body. They can find a specific gene, perhaps one that causes a hereditary disease like muscular dystrophy or sickle cell anemia. And then using CRISPR, they can precisely cut that bad gene out and even replace it with a healthy, correct version. This power forces us to make a critical choice. We can use somatic editing, which changes the genes in your own body. You would be cured of a disease, but you could still pass the original faulty gene to your children. The changes die with you. But then there is germline editing. This involves editing the genes in sperm eggs or an embryo. This change is permanent. It is not just for one person, it is for all of their descendants. We could eliminate diseases like Huntington's or Tay-Sachs from the human family tree forever. It is an incredible thought. But once we start rewriting our fundamental code, where do we draw the line? This leads us to the final, most controversial and most transformative step, the upgrade. If we have the power to fix a broken gene, What stops us from improving a normal one? This is the core idea of transhumanism, the belief that we can and should use technology to enhance the human body and mind. We could start with physical upgrades. Imagine genes for stronger bones, more efficient muscles, or lungs that can process oxygen better. Or perhaps cognitive augmentation, improving our memory, increasing our learning speed, or even raising our baseline intelligence. The tools might not just be genetic. We are already developing advanced brain-computer interfaces, or BCIs. At first, these BCIs will be a miracle for people with paralysis, allowing them to control robotic limbs or computers with their thoughts alone. But what about for everyone else? What if a BCI could connect your brain directly to the internet? You wouldn't need to search for information. You would simply know it. You could learn a new language in hours, or master a complex skill instantly. We could even expand our senses. Humans experience a tiny fraction of the world around us. We can't see an infrared like a snake or ultraviolet like a bee. We can't sense magnetic fields like a bird. With technological upgrades we could. We could give ourselves entirely new senses, experiencing a reality that is currently invisible to us. This future is dazzling, but we must walk into it with our eyes wide open. This power comes with profound responsibility and enormous risks. Who controls these technologies? Who decides what is a disease to be cured and what is an enhancement to be sold? If these upgrades are expensive, we risk creating the greatest inequality in human history. We won't just have a gap between the rich and the poor. We could create a literal genetic divide, a new species of enhanced, upgraded humans and the naturals who are left behind. How could a natural human possibly compete with someone who can think at the speed of light and doesn't get sick? This could create a biological caste system that would make all previous forms of inequality seem small. And this brings us to the final most important question. What does it mean to be human? Is our humanity defined by our limitations, our vulnerability, our mortality? Is it our struggle against these things that makes us who we are? If we eliminate struggle, disease, and even death, do we lose the very essence of ourselves? Or is our true nature to always reach further, to overcome every limit, to become something more? We are the first species to be able to consciously direct our own evolution. The choices we make in the next century will not just determine the future of our civilization, they will determine the future of our species. We arrive at last not at an end, but at a destination of understanding. Our journey has been the greatest story ever told, a narrative that stretches from the very first moment of existence to this very breath you take right now. It is a story that begins in a silence so profound it is unimaginable, in a single point of pure potential that held the promise of everything. From that first singular flash the universe unfurled. It was not a chaotic explosion in an existing space, but the sudden expansion of space itself, carrying with it the fundamental laws that would one day govern everything. For ages, this new reality was a swirling soup of energy, too hot and too dense for even light to escape. It was a universe of possibility, but it was dark. Slowly, patiently, the cosmos cooled. Energy congealed into matter, forming the first simple atoms, hydrogen and helium. These atoms drifted in the dark, drawn together by the gentle, persistent whisper of gravity. Over millions of years, they gathered into colossal clouds, collapsing under their own weight, until the pressure at their hearts ignited a new light. The first stars were born. These were not stars like our sun. They were massive, violent giants that burned bright and died young. In their fiery deaths, they became the cosmic forges that created the very elements of life. The carbon in your bones, the oxygen in your lungs, the iron in your blood, all were created in the hearts of these long-dead stars. They scattered these new gifts into the void, seeding the next generation of stars and planets with the raw materials for complexity. Our own solar system was one such beneficiary. From a cloud of interstellar dust and gas, our Earth formed. It was a violent, molten world at first, but it cooled. Water arrived, and in this chemical-rich ocean, something miraculous happened. The inert matter, forged in stars, organized itself. It began to replicate. Life had begun. For billions of years, this life remained simple content to exist. But the engine of evolution was at work. Life grew diversified and became more complex. It crawled from the sea, it learned to fly, it covered the land in green. And then, after a journey of nearly 14 billion years, that life produced a species unlike any other. A species that could not only adapt to its environment, but could for the first time reshape the environment to suit its needs. That species is us. We are the result of this unbroken chain of cosmic and biological evolution. We are the inheritors of the Big Bang. But more than that, we are the part of the story where the story itself becomes aware. This is the final, most profound contemplation. Look at your hand. Consider the mind that is processing these words. You are not just a collection of atoms, you are a collection of atoms that knows it is a collection of atoms. For all its unimaginable vastness, for its trillions of galaxies and uncounted stars, the universe was for most of its history blind and unaware. It was a magnificent mechanical dance of physics and chemistry, but there was nothing there to witness it, to feel awe, or to understand it. And then on this tiny wet rock orbiting an average star, the universe woke up. We are the means by which the cosmos achieves self-awareness. The star stuff within us, the legacy of that first fire, has organized itself into a brain complex enough to look back at the stars and understand where it came from. We are the universe's eyes, its ears, and its mind. This brings us to this great paradox of our existence. In the grand scale of the cosmos, we are impossibly small. Our planet is a pale blue dot, a mote of dust suspended in a sunbeam, as one great thinker said. Our lives are a fleeting whisper in the grand chorus of cosmic time. If our planet were to vanish tomorrow, the universe at large would not even notice. This fact should be deeply humbling, and yet in our minds we are titans. We contain a greatness that defies our physical smallness. While our bodies are confined to this planet, our minds can travel to the edge of the visible universe. We can journey backward in time to the very first second of creation. We can understand the laws that bind the stars and the particles that make up the world. We can feel love compose symphonics, ask questions about our own existence, and feel a profound connection to a reality far larger than ourselves. We are small, but we contain the infinite. To truly grasp this, to feel it in your very core, is to find a peace that surpasses all understanding. This is the silence of knowledge. It is not the politeness of an empty cold void. It is the silence of a deep forest teeming with life where everything is interconnected. When you realize that you are not separate from the universe, you are the universe, that the feeling of isolation dissolves. The fear and anxiety of being a small, fragile thing in a vast, indifferent cosmos falls away. You're not an accident. You're an inevitable, beautiful, and essential part of this grand unfolding. The same laws that hold the galaxies together are the laws that hold you together. The same atoms that burn in the farthest star are the atoms that are thinking these thoughts. You are not just living in the world, you are the world having a human experience. There is no you and it. There is only us, in the most cosmic sense of the word. As you finish this journey, let this quiet understanding settle over you. Feel the connection to the floor beneath you, the air you are breathing, and the distant silent stars overhead. You are a part of all of it, and all of it is a part of you. There is nothing to fear. There is only a story to be witnessed, a song to be heard, and a profound, peaceful connection to all things. It is the end of this story, but the beginning of your silent understanding. Good night.